Welcome to my presentation about my recent work, an origami-based shape morphing fingertip to enhance grasping stability and dexterity. I'm Zichen Kan from Hong Kong University of Science and Technology, and this project was collaborated with Yadan Zhang, Chongheng Peng, and Michael Wang. The initial idea comes from my previous gripper design last year. Due to the flat fingertips, the practical performance on payload and dexterity is limited. The similar drawback also appears on the widely used parallel grippers. If the two contact points are not well selected, the static fall equilibrium might not be achieved. In addition, this feature also restricts its dexterity on manipulations. From many researchers, it's obvious that parallel grippers are prominent in the in-hand manipulation tasks, and these operations require multiple contact states depending on the different gripper configurations, between a free spinning point contact to a firm multi-point contact. In the current solution for specific in-hand manipulation tasks, MIT group presented a series of designs for pivoting tasks of prismatic objects. In their first version design, they proposed a two-phase finger which is composed of a small hard contact point on an elastic strip mounted above a V-shaped groove. The contact states change based on the imposed gripping force and the modulus of the strip. In the improved design, by adding a pneumatic actuation, they can actively switch the geometry of the fingertip between Y shape and V shape. Some other groups try to use friction variation to get the two grasp states, like actively pneumatic inflation, passively movable ridges based on material property differentiations. In addition, lubricant is chosen to change the humidity condition of the contact surface, and a reconfigurable structure with two materials is also created. For contact surface clustering, Song has shown three typical contact primitives for the representation of major local geometries. The fingertips mounted on parallel gripper are validated on different objects with distinct geometric features and indicated stable and reachable grasps. This work brings innovations for firm grasp based on the morphology of manipulators. According to the three representatives, we try to realize the corresponding grasping approach on Morphing Fingertip and further extend the functions for the benefits of in-hand manipulations. So we propose an origami-based shape morphing fingertip design to settle the grasping stability and dexterity problems. In our design, the soft origami skeleton acts as morphing surface, and motor-driven four-bar-linkages serve as the actuation and transmission mechanism. On the end effector, there are 4 leaf facets. Each leaf facet is controlled by a servo motor independently. Multiple pole states can be achieved by permutation. All up or all down can switch to concave and convex modes. With a suitable rotating angle on opposite motors, a tilted planar mode can be generated. Due to the existence of the leaf springs, the central terrace is constrained on free rotation and the anti-actuated structure is stabilized. In the paper, we study and validate 3 morphing types that are commonly observed and essential in robotic grasping. For better mode transitions on precise control, a kinematic model is conducted, which is basically a simplified geometric model for 3 typical configurations. So, by calculation, we get the relationship between the motor rotation angle theta and the tilting angle of the facet phi. On prototyping, we combine different materials with distinct manufacturing techniques for the ease of fabrication and precise control. Soft TPU is used for the morphing surface. Hard PLA by FDM with tunable infill ratio can balance weight and strength, which is suitable for moving parts that are sensitive to inertia. Hard resin by SLA with solid infill and smooth surface is printed for parts with complex force condition and parts with a sliding motion. We conduct an angular stroke test to verify the prediction of deformed shape from proposed modeling in concave and convex modes. When the motor rotation angle is in the range of negative and positive 10 degrees, there is an approximately constant gap between two curves. This is probably due to the simplification in the modeling and conformity of motor performance. After 10 degrees, the gap increases gradually, which is because of the deformation on the soft cover of the ball joint. In the future version, the part should be changed to metal cover to prevent undesired deformation and clearance feet. Then we conduct a configuration space test in planar tilting mode to check the configuration reachability. Based on the control planar from the previous model, we guarantee that the morphing surface moving as a flat plane. A golden rod is stuck on the surface pointing to the normal direction. By sequentially tuning the facet rotation angle, the pointer tip can generate a square-shaped trajectory. In addition, we demonstrate several typical in-hand manipulations and grasping tests for contact surface fitting. We demonstrate 4 distinct implementation scenarios and make comparison experiments with conventional parallel grippers and validate the effectiveness of the morphology design, such as pivoting with convex mode, pinch with convex mode, power grasp with concave mode, and power grasp with stability test. The takeaway from this paper is it is beneficial to construct transformable end effectors to actively tackle the grasping stability and dexterity problems. The future works may consider the implementation of optimized design, motion planning, or intrinsic control of joints and end effectors. Thank you for your time, and if you have any questions, please directly email either myself or Michael Wan, which can be found at the URL of our lab.